The Prim 9 system for picturing, rotation, isolation, and masking in up to 9 dimensions. Prim 9 is an interactive data display system for exploratory multivariate data analysis, developed at the Graphic Interpretation Facility of the Stanford Linear Accelerator Center. The development of Prim 9 was a team effort. The key team members were, for optimism, innovation, and trial and error learning, John Tukey, also of Bell Laboratories and Princeton University. For implementation and programming, Marianne Fisher-Keller. They were aided at critical junctures by 3 advisors. In particle physics and production, Jerome H. Friedman. In cinematography, Stephen Levine. In editing and sound recording, Sam Stappel.
Prim 9 has been developed toward ends of very different breadth and distance. First, to learn more about what we can learn by looking at the numerical aspects of data in more than 2 aspects at a time. Second, gaining a tool for pictorial examination and dissection of particle physics data, especially data involving several body final states. Prim 9 has grown through many stages, but the evolution of display systems, like the evolution of animals, is a branching process. And so some of the abilities that are vestigial in Prim 9 may later turn out to be central for other display systems. Prim 9's emphasis is on picturing and rotation on the one hand and on masking and isolation on the other. Picturing and rotation is an essential ability, valuable alone. But the usefulness of this ability is greatly enhanced when it is combined with masking and isolation. For us, picturing means an ability to look at the data from several different directions. Rotation means, as a minimum, the ability to turn the data so that we can look at it from any direction which we choose. For picturing, Prim 9 offers us the choice of any 2 of the current coordinates as horizontal and vertical axes, 2 buttons cycling through the choices. One button interchanges the coordinates shown on the vertical direction. The other button interchanges the coordinates shown on the horizontal direction. In that way, it is easy to go from showing variables 2 and 1 to 3 and 1 to 3 and 2. Since the data we are showing at the beginning is only 3-dimensional, these are the only 3 views that we need. Just being able to see projections on all coordinate pairs can, as we have just seen, be very helpful, but it is not enough. To be able to get reasonably to all 2-dimensional projections means either a way to call for what we want or a way to move about. Since we usually do not know just what we want, and when we do, we would find it hard to learn to call for it, what we need is a way to move about. Rotations are natural movements, but which ones? We have settled for only those interrelating a pair of the current coordinate axes. A simple example rotates coordinates 1 and 2, while keeping coordinates 3, 4, and so on fixed. If we look at the 1-2 plane, it looks like this. First forward, and then backward. If instead we rotate between coordinates 3 and 1 while still looking at the 1, 2 plane, it looks like this. First in one direction, and then in the other. Here, an invisible coordinate is being rotated against one visible one. Finally, if we rotate coordinates 3 and 4, while continuing to look at the 1, 2 plane, we see no change because coordinates 1, 2, 5, 6, 7, and 8 are all being held fixed. The control of rotation is by 3 buttons, 2 of which choose the coordinates to be rotated between, while the third one drives the rotation alternately in one direction and then in the other. We can get from any one two-dimensional projection to any other relatively easily by combining these selected rotations in the correct amount and sequence. Together, choice of view and freedom to rotate do more than just give us access to any two-dimensional view. The dynamic effects of rotation let us see, not instantaneously, but at the same time, in the best sense of those words, more than 2 dimensions. This is because of the relative motions associated with parallax, with the depths of the points on the undisplayed coordinate that is involved in the rotation. We have gained much more than just flexibility by adding rotation. Here is an artificial set of points where rotation easily shows us much more than a collection of static two-dimensional views. We look at just a few views, the 2-1, the 3-1, the 4-1, the 4-2, the 5-2, the 6-2. If we looked at the rest of the 28 views, they would all look generally similar, a more or less roughly spherical cluster of points in 8 dimensions. To find out more easily where we want to rotate it, I now add a picture that shows where the original axes lie in terms of current coordinates. The next thing to do is to move old axis 4 out to join old axes 1 and 3, and then to move old axis 6 out to join 5 and 7, and then old axis 8 out to join the 3 of those. When they're all in position, you can see that this is the same data set that we saw before, which is really an 8-dimensional spherical cloud of points with a slot cut right across it in a direction that does not show in any of the original 2-coordinate views. Statisticians tend to think of multidimensional data as made up of structureless blurs. The example you will now see shows that, at least in the simplest cases, the data of particle physics has much more structure. This 4-dimensional physics data, which you will also see again shortly, seems rather structureless until we rotate it. To take advantage of this kind of structure, a simple thing to do is to mask out some of the points. Specifically, to mask out all points, one of whose current coordinates fails to satisfy one of a family of simple inequalities. We can see what this does with a new example. This view shows what happens when the masked coordinate is visible and the lower cutoff advances from the left steadily. And then retreats. If the masked variable is not one of the two we are looking at, other interesting things can happen, as we will see when we mask the same data on its third coordinate. Again, as the mask retreats, we come back to the original view. Prim 9 allows masking from either direction on each or all of the current coordinates, separately or together. Control is by 4 buttons. One button turns the masking on or off. A second selects the coordinate whose masks are to be adjusted. A third selects whether the low cutoff, the high cutoff, or both are to move. The fourth drives the motion, alternately one way and the other. The flexibility of Prim 9's masking is limited, like the flexibility of its rotation, so that it is easy to control and so that we can understand what we want to do. Masking is tied to coordinates. If we rotate the points, different points will be masked out. This has its real usefulness, but we do not always want to have it happen. Often we want to isolate one or more sets of data points and then have the ability to bring back any such subset and then do anything to it that we could to the whole data. In Prim 9, isolation starts with masking. We can use masking to identify the data points to be isolated, something that can be done repeatedly. Let us go back to our first simple example and first mask and then isolate using it as a test bed. Here we are masking from one side. Now we can mask from the other side. Now we can isolate the piece we have just masked. As we see when we turn the mask off. If we rotate this, it will rotate just as before. If we like, we can get the complement to the piece, and it will rotate when called for in any interesting way. Thus, we have isolation and full control after we have isolated. We are now ready to illustrate Prim 9's use on some simple particle physics data. This data was taken here at SLAC in the 82-inch bubble chamber, and it involves 500 events in which a 12 billion volt K plus meson struck a proton and produced exactly these three products: a recoil proton, a pi plus meson, and a K0 meson. For each product, 3 components of momentum were measured so that there were experimentally 9 numbers which describe the event completely. But since each of 3 components of momentum must be conserved, the 9 can be reduced to 6. Since energy is conserved, the 6 can be reduced to 5. And since the whole situation is symmetrical around the direction from which the K plus meson came, the 5 can be reduced to 4. The particular 4 coordinates that we will use in the beginning of the display are all of the form the energy of one particle plus or minus the energy of another squared, minus a corresponding expression in the momenta where the square is to be taken as a dot product. Here we have the first two coordinates that we just described, coordinates 3 and 1, 3 and 2, 4 and 2, 4 and 3, 4 and 1, and back to 2 and 1. We can already see that the general structure of this data is like an example already described by Pless, in which there appear to be 3 rods of points. This will become clearer if we make a rotation from this position, when we can see one rod gathering itself into a single group right here at the bottom of the picture. Now, the natural thing to do first is to try to isolate this blob at the bottom, which corresponds to a rod which we are looking down endwise. We can do this by turning on the mask and bringing a mask downward from above. And you can see the points beginning to be masked out. Once they are masked out, we can isolate them. Now, if we turn the mask off, it's easy to rotate these points and see what we seem to have. Here is one rotation. Here another. Here a third. And here a fourth. No matter how we rotate this set of points, they look rod-shaped. That means that all these points are close to a single line in 4 dimensions. If we come back to the place where we had isolated these, it is now natural to go ahead and prepare to look not at these points, but at all the other points in the picture, which look like this. The next natural step is to have a mask move in from the right so as to isolate this vertical stripe of points here. Once this has been done, we can go ahead to the isolation. And now when we try to rotate these points, we discover that they are not a rod in 4 dimensions. They appeared to be a rod in one projection. But if we rotate them around enough, we see that they have considerable structure. And in fact, they have somewhat the 3-rod structure themselves when they're shown in this position. Having gone this far, we are now ready to go back and remove this last rod. And if we come back to the original position, we see this grouping, which can now be itself rotated. And again, we see a somewhat similar but weaker structure in which there is a concentration down at the bottom, which corresponds to something at right angles to the screen, and a couple of faint bars here. The net result of breaking up our original picture then is to show what looked like one rod and some strays as a three-part configuration, to show what looked like another rod as another three-part configuration, and to show the third apparent rod as an actual rod. Thus, it would appear that while if we look at the original picture with which we started things here, we might have thought that there were three rods. We are now prepared to believe that there are at least seven. This is an example, then, of what can be done with the simple data to see more than you would be able to see by any simple approach that just involved rotating the whole data. Because what we saw in the second and third parts was very much clearer because we could look at these parts separately. Prim 9 is now ready to examine and dissect particle physics data. Its direct value for this purpose will have to be learned by experience. What have we learned from its development beyond a reasoned conviction that pictorial systems, to be effective, must go through many stages of trial and error learning as it did? What have we learned that will be useful at other locations? We now understand that the details of control can make or break such a system. We now recognize that these details of control must be adapted to what is available and to the people who are to use the system. If we had had 10 knobs and 6 switches instead of 32 buttons and a light pen, we could and would have realized the same 4 essentials in a quite different way. We now recognize the great value of such dynamic aspects of the display, especially easily recognizable rotation. 2 aspects, horizontal and vertical, are always before us. What third aspect supports them best? We now have a strong feeling, almost but not quite a conviction, that the dynamic aspects of rotation are extremely valuable, more useful than stereoscopy, color, flicker, or distinctive characters. We have learned that this sort of pictorial facility can be useful in 2 quite different ways. First, directly, and second, as a source of ideas and approaches. Ideas and approaches that can guide algorithms for experimental programs to chew over numerical data in a batch mode. The first of these chewing over programs is now in an advanced state of development. Others can be expected to follow. Finally, and above all, we have learned that the 4 essentials of picturing, rotation, isolation, and masking need to work together, and that from them we can learn much.